Hi all, this is Claudio from ANSYS with the third lesson from the series ANSYS FEA from basics to advanced. A short reminder about my website expertfea.com with lots of simulations, tutorials and instant FEA support. Also make sure to join me on Patreon if you want to see and watch newer and advanced simulations. Here you have a sneak peek from those live streams that I have sustained in the recent months, and they will be available if you become a subscriber on Patreon. So, as I promised in the second lesson, I would like to initiate you in how to break material, and we are using a very simple tension scenario. Here there are some cases that I have studied today to ensure a proper and reliable approach for the breaking, and let me lead you on the proper path. So, firstly, I would like to remind you that in static structure and transient structure, being implicit finite element analysis, breakage or erosion does not happen or occur. Instead, we need to appeal to what we know as being explicit dynamics, and let me tell you why. Having known the main equation for how the FEA is working, so the external forces must be in equilibrium with force given by the acceleration, by speed, and the stiffness and displacement. All right, the implicit simulation solves the displacement as this equation over x, over the stiffness. Let me write it here. So it solves for x, which is the external force, minus the applied force minus the other force, over k, which is stiffness, the stiffness matrix. When we, and if we make somehow this k, if it would happen for an element to disappear or to be eroded, the stiffness of the matrix at that point, in that point, would become 0. And you can see in this equation that we would have x over something, x equals something over, let's say, 0, which would be impossible, yeah? Because here would tend to 0 under the fraction. And this would be impossible to be solved by the solver, by the implicit solver. On the other hand, when using an explicit solver, we are solving, the solver solves and finds out the acceleration. The term with the stiffness, which is responsible for the deletion of the element, this term might become 0 because the k or the stiffness becomes 0, and it does not interfere with our solving. Let me write this down. Acceleration equals this fraction, f external whatever minus cv minus kx over the mass. And when this term goes to 0, there is no problem. For the equation to be solved, only having fx minus damping and speed over mass. And there is no problem with the mass if one element is deleted or a few elements. There is no problem, it's neglectable. This can be solved easily by explicit, not by implicit. This cannot be solved by implicit if X, or the stiffness, the integrity of the matrix, yeah, is affected and the K equals 0. This is why we are going to use an explicit approach, yeah? The conclusion is here, we solve for displacement, and if the K is 0, being under the fraction line, then there is an error. If the Kx equals 0, then the math continues here. So, I explained to you why I went for explicit dynamics. Let me go and initiate such simulation. A short reminder, a value, yeah, at break would be around, let's say, 1217 strain, and over 300, let's say, megapascals to achieve breakage. These are the limits given by the supplier, the material supplier. So we are in explicit dynamics. What are we going to do here? It is asking us, it shows us an error here. There is a question mark. Let's click and try and find out why there is a question mark. Because in analysis settings, we need to input an end time. From now on, our simulation is dependent on time. Time is important. If we were, for example, to hit here 1 second, let's say, as it were in the past simulations, we had 1 second, there was only one solving step. If we were to hit here end time and not do anything else, let's just solve. Let's see what happens. So it says, for example, failed too many nodes per element. Why is saying this? Because we're using the default mesh type inherited from static structure, but in reality we should change the physics preference to explicit. In mechanical, we're using a second order mesh with so-called mid-side nodes, and in explicit we do not have mid-side nodes. This is a first order type of mesh. So let's solve again. How does the mesh look like? It's like this. And the FEA works. Let's see. If we were to use 1 second, the FEA would take 3.2 hours. But I would like to wrap this lesson under 20 minutes. So let's begin kind of cutting and simplifying the simulation while hopefully holding the same request from the simulation. All right, let's stop this. And the easiest way is if we divide the end time with the value. Let's see what we obtain. If we divide 1 second over 10, we would obtain 0.3 hours. But I would like to have it much faster. So, for example, let's use a fraction of what we had. If we keep this end time here for 1 second, then we would have a realism of the load. I'm telling you because when I'm using a fraction of the time, this force applied on this end will be a sudden force. It will be explosive and it will create a shock wave, let's say, due to the suddenness, let's say, due to the small time event, let's say. I predict that there will be a problem using such a small time and such a big force. By the way, the force always should start with 0. And let's stick to what we had in the past, 50,000 Newton. The force should not, the FEA should not start with a value, alright? It should increase from 0. At this moment, let me save and solve. Surely the solving time will decrease very much. So instead of 3 hours, it will be around 40 seconds. Only with this caveat that having such a short end time, the caveat is that this force imposes a shock. It's a sudden force. It's not the force that were used with during the hypothesis of small deformation in strength of materials. It's not the same effect as it was in the static structure simulation. Let me show it to you. Firstly, I think we have an error. Yeah, energy error too large. So, there is something. As I told you, there is a shock, and the force is applied only in this area. But it's a sudden appliance, a sudden occurrence of force. There is a plastic strain, but only localized here. Very high strain localized here due to the very short application, very fast application of the force. Instead, we would like to have more plastic strain, elastic strain, and directional deformation in the entire beam. At this moment, we cannot continue with this approach using force. So my suggestion is, let's right-click suppress, and instead let's help the solver with a displacement. Let's pull the same face. With, for example, I ran some tests. Let's pull it with 60 millimeters. And 60 millimeters compared with 150 is 40%. Why I'm saying this? Because I would like to evaluate and to obtain something around 40% the total strain, if possible. So let's solve. Let me remind you the material. We do have the nonlinear alloy with tangent modulus defined. You remember? There should also be a graph, a plot. I have shown it to you in the past lesson. The bilinearity plot of stress and strain. And at this time, let's solve. All right. So in order to see results during the simulation, we do have this, the so-called trackers, and we can right-click, switch to automatic mode. But this for the next solver. All right, so what do we have? We have the applied displacement, 60 millimeters. Yes, 60 millimeters also here. We do have some elastic strain. By the way, do you see that this curve looks like the bilinear curve from the material that we defined? Yeah, it's like here we have the elastic domain and here we have the plastic domain. Yeah, it looks similar to the bilinear isotropic hardening curve. Look at the plastic strain. It is somehow around the value that I said before. I would like to have a strain around 40%. And if we add 0.35 with 0.006, let's say we do, and we are around the 0.4 value. Now regarding the stress, we can see that the stress is much higher than the breaking limit. Now the question that arises is why we do not have a breakage. There are multiple answers. Firstly, because we were so stubborn to use this material, let's try and make this material break. But normally, we should not use such material in explicit dynamics when asking for fracture or for breakage. We should not use such a material because it's not sufficiently defined. It does not have a damage model. It does not have a failure criteria. But because we are here, we'll do our best to make it work and fracture occur. So our option is this one. The software by default lets the part, the mesh, whatever, lets it stretch 150%. 150% over 100, yeah, is 1.5. This is too much, let's say. We know that the expected strain should be around 0.5. So let's put a value that's 0.4, I'm sorry. Let's put a value before 0.4 in order for the FEA, for the mesh to break when it reaches 0.4. Yeah? For example, let's assign 0.35. And if we are correct, at this value, at this strain, the material should break. So let's save. Let's solve. So I have assigned some trackers. This means we can see live what happens with the simulation values. We see the extension, we see the stress as it increases, and you can see here there was a maximum there, yes? Let's save. So I promised fracture, this is fracture. Yes? Let's animate. Additional deformation, elastic strain as we had before, plastic strain. This is the value. And because we exceeded the 0.35 for the maximal allowable strain, and we do have a total of around 0.35, let's say we exceeded this value, then we have a breakage. We know that there is breakage because we also exceeded the stress outbreak, yeah? The stress outbreak was around 310, and we exceeded this value. Now the question is this the best model? Is this the most reliable? Yes and no. So, normally for the next lesson, we should use a proper material, a better material than this, would be linear isotropic hardening, and we should obtain, let's make this 0, we should obtain the necking. This is a very sudden break, and we do not have a clear necking here, and we are expecting for a necking. So this material or this simulation is kind of good to impress some beginners, let's say, but it's not very proper and reliable. So it is a start, but it's not the best option regarding the mathematical apparatus and the FEA approach. So join me in the next lesson for a better, optimal and justified approach for the same simulation with a better failure criterion and necking and overall better behavior. That's all for today. Thank you, and join me in the next lesson. Bye-bye.